Okay, so very fast I'm going to introduce you the Enogia company. It is a small French company founded in 2009 by 4 engineers, and it is devoted to work on the organic Rankine cycle, especially at smaller scale. Right now we are approximately 20 people and generating 1 million turnover, and we have references of ORC systems in 9 countries. We also happen to have a strategic partnership with the IFP Institute, which is a French petroleum institute, and which gives us backing on technological and marketing stuff. A little bit history about our company. Since we were founded in 2009, we developed the first expander prototype. Then we worked on the small scale ORC demonstrator. Here is a picture of our very first unit, which was in a standard house. We didn't even have company premises back then. Then we had a successful fundraiser with business angels from the Arts et Métiers schools, which is a famous engineering school in France. We developed our ORC technology and we had a growth the last few years, which makes us now a small company with 24 ORC working in 9 countries. So you have a few pictures about the work we've done so far. But before going deeper in the technological development, I wanted you to introduce the context of these works. And as I am not a UK citizen, but a French citizen, I'm going to use French numbers of the ADEME, which is a French energy agency, to explain you a little bit about what is the situation of waste heat in French industry. So if you take the fuel power, the primary power of the fuel used in the industry, you happen to have a useful process thermal power that will really be used for a purpose in the industry process. And then you have heat losses. And very often when I speak to industrial people, I happen to say that I don't want to install ORC in industrial situation because the best way to make energetic efficiency in industry is first to avoid the heat losses. So if you avoid the heat losses, then you don't need to recover, and then you don't need to generate power with ORC. Then the second best thing to do is to recover the heat losses and to use directly as thermal energy. And the last thing to do is to recover the heat and to convert by means of ORC or TFC into electricity. So basically, it feels very weird, but I often say it is a good way not to use ORC when you can make good use of the thermal energy before. And then in the end, when you've considered all the different solutions to energetic efficiency in industry, you happen to have a very small amount of non-recoverable final heat, a very diffuse streams that you cannot recover. The ADEME, the French Agency for Energy, made a study of the industrial waste heat streams and published in 2015 the result of this study. It is very interesting. The first, you can see on the right, that is a graph of where the energy is lost in different industries. And an interesting thing is that it is fairly well reparted in different industry sectors. As it is written in French, I will translate. So the yellow on top is the chemical plastic industry. Then just under it, you have the metallical industry, but with non-ferrous materials. Then the green one is food industry, and you can see also in France the food industry is quite strong. And then the blue one is ferrous industry, and the gray one is paper industry, which also has very high energy losses. Then the violet one is refinery, the petrochemical industry, and you've got the other industries in blue. So you can see it is fairly well reparted. There is no sector that is better compared to another in terms of energetic efficiency in France. All sectors have fairly high losses. And then if you take another analysis by the temperature, that is a graph at the left, you can see that the energy losses are the bigger at the lower temperatures. Interestingly, this graph begins at 100 degrees to 200 degrees, and there is no study of the heat available under 100 degrees. And I think personally that this is a very sad thing to this study, because heat losses under 100 degrees are enormous, and I think Jeremy will concur to this. But still, you can see there is a curve of growing available energy when you go to the lower temperatures. The global amount of energy lost in French industry may be quite similar to UK industry, as you have terawatt hours per year on the lower scale, and it is fairly similar to the numbers we saw just before. So if we put on a graph of temperatures the different waste heat streams, the ADEME considered you can categorize 3 types of heat streams. You have the liquid streams, where the heat is on liquid medium. You have the gaseous streams, like the exhaust gases. And you have the diffuse streams, that are basically the streams that are not possible to recover. And on this graph, they try to put every stream they discovered in the French industry in regard to temperature and to type of waste stream. So at the lower temperatures, you have the cooling waters, and this was a very interesting example that was in the previous presentation about the cooling towers. Very often the cooling towers waters are between 30 and 70 degrees. Then you have the higher level temperature of cooling waters between 70 and 90 degrees. And it happens that most of these waters are found in food, paper, and chemical industries in France. If you go higher on liquid, you have the higher temperature liquid, which are often superheated water or thermal oil, and they come very often from furnace cooling. If you go on the gaseous scale, the lower temperature gaseous streams are drying air or compressor air, which is lower temperature than the exhaust streams. Then you have process steam, and then you have exhaust gases on the higher temperature scales. And then you have the diffuse streams that are mainly the bad insulation or ray emissions, and that are the streams that are not possible to recover. Okay, so now that I've shown you the state of the heat losses in French industry, I want to introduce Enogia work on the low temperature, small scale ORC system development. And just for you to understand, when we started the company, we were very low on budget, as every startup company is, and we started to work on the smaller scale of the product we wanted to develop, that is a 10 kilowatt electrical ORC device. So basically, an organic Rankine cycle, I guess many of you know how it works. It is a very similar process to the Rankine cycle that is used in most of the power plants in the world. In an organic Rankine cycle, you take a refrigerant, you make it under pressure with a feed pump, and then you vaporize it in contact to the waste heat source in the evaporator exchanger. Here on this graph, it is a plate heat exchanger, but it can be any technology. It's up to the company or the design team which makes the process. Then you have a turbine expander, which expands the refrigerant, and you draw out the mechanical power to generate electricity. And that's really the goal of the organic Rankine cycle. But in order to close the cycle, you need to condense and draw out the thermal energy by a cooling method. That is a condenser. And so here you have the traditional organic Rankine cycle. The critical part about the small-scale organic Rankine cycle is the expander, because as you've seen in the previous picture, I took off-the-shelf pictures at different manufacturers. You can find many exchangers, you can find many pump manufacturers, but you cannot find any off-the-shelf expander for Rankine cycle systems. The problem about this expander is that it has many antagonistic parameters. It needs to be efficient, but it needs to be small. And very often, when you make very efficient systems, you happen to have larger systems because you want to reach better performance, lower temperature pinches. In a case of electrical generator, you might want bigger magnet, more copper. It needs to be cheap, which is also going against efficient, because the most efficient you will use higher cost manufacturing processes. And it needs to be reliable, which also goes against the cheapness of such a device. So, in order to balance all these parameters and develop a product that is really useful for an industry or the energy sector, you must have an optimization function. And what we choose was to balance the total lifetime ownership cost of the product compared to the total benefit of the product, which is basically the electricity production multiplied by the price of electricity. And the interesting thing is that we are considering the total ownership cost over the lifetime and not the capex. And because it is very important, this product will run maybe 6,000 hours a year like we saw, maybe 8,000 hours a year. And if it has high OPEX, then this product will not be interesting for the customer. So Enogia chose to develop an expander based on the kinetic turbine technology because it is a proven concept on larger scale ORC units and it has no friction, no wear. And we also choose to include the permanent magnetic motor inside of an hermetic housing within the turbine generator because this allows to get rid of the mechanical shaft seal. And to get rid of the mechanical shaft seal is a key point we wanted to achieve because a mechanical shaft seal makes fluid leaking, so you have to replace the working fluid. And it also makes maintenance because you have to replace the mechanical shaft seal. So we succeeded in developing a small-scale ORC expander with no mechanical shaft seal, with a kinetic turbine and a permanent magnet generator connected together in a single housing. And here you can have a picture of it. Another very important thing in regard to the kinetic turbine choice and in regard to low temperature ORC applications is the fact that the volumetric expanders have limited volumetric capacity. And so when you are running at lower temperature, you have higher volumetric flows. And so the good thing about the turbine unit is that we developed it so it can reach full power in an ORC situation with 80 degrees centigrade hot water inlet running in a loop. I am not speaking of similar things like the TFC, where you want to recover all the thermal energy out of cooling water source down to 30 degrees. I am speaking more of the cooling loops that would be running in a closed loop from 80 to 70 degrees centigrade closed loop, like an engine loop. So it is very complementary technology. In one case, you want to recover all the sensible heat on an open loop, then it is better maybe to use the TFC. In another case, you are on a cooling loop that is closed, then the ORC could be a better solution if you can work with a return temperature of 70 degrees. And then, compared to volumetric expander, the turbine has a very interesting feature that it can reach full power at low temperature because of the high volumetric capacity it has. So the development of a small turbine expanders go through the traditional development scheme we have at Enogia. We go from preliminary design to CAD design to drawing and prototype manufacturing. From 2009 to 2015, 6 generations of small 10 kilowatt turbines were developed. Here you have the pictures of it. And now we have a many commercial experience on this product, from wasted to power, mostly on anaerobic digestion, but on other processes with 90 to 80 degrees inlet and with 70 degrees return temperatures. Here you can see an anaerobic digestion farm in Italy equipped with the Enogia technology. This one is in France, and those are other premises of our customers. So the satisfying performance is 5 to 7% electrical efficiency depending on inlet-outlet conditions for hot water. And when I say satisfying, it may seem a low efficiency, but please remember this is wasted and we are bound by Carnot's law that Jeremy shown to us. So we cannot achieve very high efficiency. And we are generating out of waste stream, so it is very useful even if you reach low efficiency. Here is a case of an anaerobic digestion ORC with 100 kilowatt inlet and 6 kilowatt outlet, electrical outlet. So is really a market for 10 kilowatt ORC system in the industry? I don't think so. And we thought that a 100 kilowatt size would be much better for the industry. And we analyzed the competitors in the ORC field, which show that there is very little offering on a very low ORC temperature for 100 kilowatt. So we worked on a new turbine design, which is called the 100 LT for low temperature. On low temperature, it is small enthalpy drop for ORC turbine, but it is a high enthalpy drop for a single stage. And so we chose a radial stage because it can leave us subsonic turbine with this enthalpy drop, and then the efficiency is very good. And because we had not off-the-shelf electric generators and power electronics, our partner IFPEN and Mavel Powertrain in Italy developed for us a custom unit, which you can see at the right side. The result is the Energia 100 LT turbo generator, which is maybe one of the most compact units in the world, only 60 centimeters long and less than 100 kilograms, including the generator. And it measures promising performance on its test rig at 70% isentropic multiplied by mechanical and multiplied by electrical efficiencies. So this is what we call total turbine efficiency at Energia, and it is quite good numbers. We installed this unit on an anaerobic digestion power plant in France, running on low temperature engine heat. And you can see it is very simple to install with 2 water houses, 1 electrical cable. And a very nice feature of this unit and of the evaporating scheme in the ORC is that the return temperature to engine is very stable. The goal is to reach 68 degrees, and here on this graph you can see the oscillation is not more than 1 degree. This is mandatory for engine lifetime in anaerobic digestion plants. So the current product offering goes from 10 to 100 kilowatt. I'm going to speed up. This is a 40 kilowatt using hot water near Paris. So I show to you that most of the hot water streams and heat stream lots are in the lower than 200 degrees. That we developed a cost-efficient ORC for low temperature hot water, and now it's part of the Energia product range at NO 100 LT unit. And we are looking forward any project in low temperature heat to power generation with any of you. And thanks a lot for your attention.